Okay, welcome back. Chemistry 3202 course overview. Unit 1, Section 2, Lesson 2, Factors Affecting Equilibrium. And working in with Lesson 2, we'll be dealing with Lesson 3, Le Chatelier's principle as well. Here's a list of the textbook readings and a few practice problems. Looking at this little picture here of this unknown cat and his little boy, what we notice about this is that these two characters are in a state of balance. All right, as we've been talking about in the last lesson, they're in a state of equilibrium or balance, and right now they're pretty good. But if I was to give one of these guys a little tickle or a nudge under this right side of his body and give him a little push towards the left, ultimately you know how he's going to respond. He's going to try and push back to try and regain his balance. All right, so that's what we're looking at in this lesson. How can we upset the balance of a chemical reaction? And then how is that chemical reaction or equilibrium system going to respond to try and restore its original state of balance, or at least some kind of balance, so that it won't topple over and go all the way in one direction? So that's what we're looking at in this lesson. Okay, the position of equilibrium. When we look at a system that's in a state of equilibrium, remember the definition of equilibrium was where the forward and reverse rates of reaction were equal. The rate going forward was equal to the rate that was going in reverse. It said nothing of the concentrations. It made no reference to the concentrations being equal. In fact, in almost all cases of equilibrium, the concentrations are never going to equal. They're going to be unequal in most cases. So what we're looking at here is the idea that the concentrations of the reactants are either going to be greater than the products, or the reactants are going to be less than the products, depending on what position the equilibrium has taken. Okay, so once again, the only thing that's equal in equilibrium is the forward rate and the reverse rate. So we want to look at this idea of a position of equilibrium. So what we're looking at here then is the position of equilibrium depends on the relative concentrations of what's in the bottle at any given time. So if we have a bottle with 4 reactants, say reactants A, B, and going to products C and D, we want to look at the relative amounts or the relative concentration of each of these reactants and products at any given time during the equilibrium. And what we're looking at is this idea that if the concentration of the reactants is greater than the concentration of the products, then we say that the position of equilibrium lies to the left, or it favors the reactant. So let's have a look at that and see what it is we're talking about. So if we had to look at the contents of this jar and say, okay, if this system was in a state of equilibrium and their equilibrium favored being pushed in this direction. So if we looked at that cat balancing on the log over the river, he'd be tipping more than one side than the other. So what this is representing is the side that this reaction system is tipping towards. So in other words, as this reaction goes back and forth, it's going to be producing more A and B relative to the amount of C and D that's in the container. So what we're saying here is the reactants are favored because they're a larger concentration, and the equilibrium is going to lie to the left. Now if we could do this graphically, you know, we represented equilibrium last time with a graph. What we're seeing then is that as equilibrium is approached and it begins to level off, it's not really this area here before equilibrium that we're concerned about. What we're interested in is what are the relative amounts or concentrations. So if this was concentrations on the y-axis here, we want to be able to look at the relative concentration of A and B versus C and D. So A and B are the reactants. So what we're saying, once this equilibrium is achieved, we know that equilibrium is established because it levels off and the concentrations now become stable. But the concentrations of A and B have stabilized at a much higher level than C and D. So we would say the reactants are favored. The concentration is higher at equilibrium. If the opposite was true, if we looked at this particular system and we said that the products were greater, what would happen here now is the system would shift in the other direction. And we would say, okay, if the products are favored, this equilibrium would be tipping to the right-hand side here now, so the cat would start to shift to the right as he walked across the log. And if it's going to shift to the right, if the forward reaction is favored more than the reverse, then we would see that the concentrations of C and D would be much larger once they regain their balance. All right, so if this was the guys on the log there, they would be tipping further to the right in order to maintain their balance. So that's what's happening here. This reaction is tipping to the right in order to achieve a balance. And if we looked at this graphically, we would see then that this is a situation where the concentrations would intersect. Because as they're approaching a sense of balance, this is where we achieve a balance here. This is equilibrium, where they level off. So as we're approaching this sense of balance, what's happening is more and more product is being formed. The concentration of products is much larger than the reactants. Hence, we say that the products have been favored because the product concentration, once we reach the balance, is much larger. So that's what we refer to as the position of equilibrium. Either the equilibrium favors the reverse reaction, in which case the reactants are favored, or the position of equilibrium favors the forward reaction and the products are favored. So the question comes up then, how can we change the position of an equilibrium system? Once a system is at a state of balance, how do we go about upsetting the balance so that the system has to try and come up with a new balance? And we're saying that as long as the system is in a closed container, as long as nothing is added and nothing's removed, it's not going to want to shift. And two conditions here: it has to be a closed system, and the temperature and pressure have to be kept constant. So we can't fluctuate the temperature. The air pressure inside the container or the pressure of the contents has to remain constant. As long as these things are constant and we have a closed system, then the system is never going to want to shift. It's going to be in a nice content sense of balance here. So if these are the things that we would need to do to make sure that the system stay at balance, then these would be the things that we could start disrupting to say, hey, let's change the temperature. Let's change the pressure. Let's change the amount of material inside the container. Let's open it up. Let's let some escape. Let's open it up. Let's pump some more in. Okay? So here are three things then that we can do to shift the balance of an equilibrium system. We could change the concentration, i.e. by opening up the container, adding more, or taking some away. We could change the volume of the system. So if we had it in a flexible container, we could squeeze the container together and make a smaller volume, or we could stretch the container to make a larger volume. And number three, if we change the temperature, then we can affect the position of equilibrium. Now in the case of concentration, that's only going to be if we change it for gases or aqueous solutions. It will not work for solids or liquids. And we'll talk about that now in a sec. So a fellow by the name of Le Chetalier, hence Le Chatelier's principle, was looking at this and he's saying, yeah, well, let's see what's going to happen when we're going to start disrupting things. Let's push something to the right. Let's push it to the left. That cat's on that log. Let's give him a nudge to the left. How is he going to respond? What's the basic reaction, or how is it going to respond to try and maintain balance? And this is dealt with on page 520 of your textbook if you want some more background reading. And Le Chatelier's principle simply says that if a system at equilibrium, so a system that's in a state of balance right now, is subjected to some kind of stress, change in concentration or a change in volume or a change in temperature, the equilibrium is going to shift to try and maintain a new balance by trying to relieve that stress. Give me an example. All right. You're in a room, it's very, very hot, you're sitting down with your winter jacket on, zipped up to your throat, and the teacher comes in and turns up the thermostat. It gets very, very hot in your room. You respond by trying to cool yourself off by taking off your winter jacket, right? So your stress is that it's hot. The relief to your stress is to try and make yourself cooler again. So everything is like an opposite reaction. You push left, I push back right to try and counteract that balance. So the system is looking for some kind of new balance. It may not be exactly where it was before, but it's going to be some kind of new balance. Okay? So what we're looking at then, if a system is in a state of balance and we try to upset the balance, we're going to try and counteract that upset to try and get to a new state of balance. And the idea behind this is that if we start shifting and changing to try and get a new balance, then that's just exactly what we've done. We've went to a new happy place. We're currently in a happy place. I've made you uncomfortable. You try and get to a new happy place, right? You take off your jacket so you cool off, right? That's your new happy place. So the consequence then is that everything else in the system is now going to be affected. Because if you upset one thing, then everything else has to try and compensate to get everything back to some kind of balance, because everything is interconnected here. Okay? So let's have a look at some examples. Here's an example of concentration. And we want to look at this from a couple different perspectives here. So we're saying from the collision theory, remember, if particles collide with the correct orientation and the correct energy, then you're going to get a successful reaction. So the collision theory is saying, all right, if you increase the concentration of one of the reactants, then you're going to increase the number of collisions. More collisions means the forward reaction is going to go quicker. Likewise, if I increase the concentration of, say, a product, then the products are going to start colliding more often, and we're going to get more successful reverse reactions, so the system will shift backwards more. So that's the collision theory. What Le Chetalier would say about this is he would say something to the effect that, okay, if I add a reactant, then the system is going to respond by trying to get rid of that excess. And as a result, it's going to shift in a direction to try and relieve that excess amount. So for instance, if I looked at a chemical reaction here where we had two reactants, A plus B, giving products C and D, and let's say we subject it to a stress. Let's say we open up the container and we put in some more B, whatever B is, a gas or an aqueous solution, doesn't matter. Let's just say we put in some more B. So here's a situation whereby the concentration of B gets much bigger than it was originally. It's now no longer in a happy place. It was happy, now all of a sudden we've stressed it out. So the system is looking at this and saying, well, too much B, too much B, too much B, we got to get rid of B. Now the only way it can get rid of B is by going in this direction. We want to get rid of that excess B. So the reaction system, the equilibrium system, is going to shift forward to try and get B back to normal. It's trying to get B small again. Now the consequences of getting B small again means we shifted forward. The consequences of that is that now C is going to go up a little tiny bit, D is going to go up a little tiny bit, and at the same time, A has to drop because we shifted forward. So you notice that everything has a consequence to the effects of adding B to this container. The collision theory would say, all right, we've increased the amount of B, so we made more collisions between A and B, so that means the forward reaction is going to be faster because there's going to be more collisions between A and B than there are between C and D. And that's what the collision theory is saying. And it's going to do that until it reduces the amount of collisions between A and B, trying to get those collisions back to normal. And the consequences, of course, is that C and D will increase slightly and A will decrease. So these are the consequences or the effects of achieving the new balance. Okay, no matter how you look at it, either from Le Chatelier's principle, the stress, the response, the result, or from the collision theory, the effects would be the same. If we look at this graphically and say, okay, what's going on here from a graphical perspective, and you see these sometimes on the public exam with saying, okay, the stress is that we've added B. So all of a sudden A, B, C, and D, they're all in their happy place. They're all at this equilibrium because their concentrations are not changing. They're nice and stable. All of a sudden we come along and say, oh, let's drop some more B in there. So if the concentration of B all of a sudden spikes, all right, so I'm going to refer to that as a spike. Okay, so this is going to be a spike in the concentration. All right. What we're going to notice here is that Okay, well, what's the consequence of adding B to this reaction vessel? And the consequence is the reaction wants to try and reduce this to get rid of it. It wants to try and get it back to some normal level. Now, of course, it's never going to get back to where it originally was. There's always going to be slightly more at this new equilibrium than what it was here. So, let me just get rid of that for a little bit there. I just want to show you what the effect is, of course. The effect is that B begins to drop. Nice little curve here. The effects of that was that, okay, A has to go down as well because the reaction's moving forward. The effects on C and D is that C begins to rise, and so does D begin to rise. Until eventually, of course, we reach a new equilibrium where it levels off again. Levels off, levels off. And all of a sudden, we're looking at this and saying, hey, we're now at a happy place because everything is now in a state of constant balance. So what we're saying then is that there's an adjustment period here, the time when everything is starting to get to its new happy place or its new equilibrium. And we know that we have a new equilibrium because the concentrations are now stable. They're not changing anymore. And we can see that everything is stable once again. And we have a new position for the equilibrium. And you notice we're not back to where we were before. Everything had to accommodate to take into account all of that extra B that was added. And that's a graphical depiction. Here's some more examples, quick ones. Let's see what happens here if we make D larger. So we can either, we can open up this container and say, let's make D larger this time. So if we increase the concentration of D, Le Chetalier would say, hey, that's a stress. The system wants to get rid of that stress. The only way it can get rid of the stress is to get going in that direction this time. The effects of this one is that, hey, if we're going to go in reverse to get rid of D, then C goes down as a consequence, B begins to get larger, and A begins to get larger. So that's what Le Chetalier would say. He's saying, all right, stress is D is larger. The response is to try and get rid of the excess D. The result is that it shifts in the reverse direction. C decreases, A and B will increase as well. Collision theory simply says by adding more D, we're increasing the number of collisions between C and D. More of the reverse reactions are happening more quickly, and therefore the reaction shifts back. Speeds up the reverse reaction rate. Okay, another example. What happens this time if we removed one of these? Well, it's the opposite effect. If we made A, if we're going to take A out of this container and make A really, 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 really tiny. Let's make A really tiny. Here we go. A is tiny now. The system's saying, oh, that's a stress. I don't want A that small. That's too small for A. We need A to be bigger. All right, so the system is looking at this and saying, let's get A larger. So the only way we can make A larger is by shifting back that way. The consequences of shifting back that way is that the concentration of B will go up and C and D will begin to drop. Okay, so again, consequences for every shift. Le Chetalier would say A is the removal of A is a stress. The system responds to try and replace the lost A. The result is that A increases, because that's what we wanted to do in the beginning, get A bigger. But because of that, everything else shifts as well. So B goes up and C and D decrease. Collision theory would say if we reduce the amount of A, we've got fewer collisions between A and B, so the forward rate of reaction slows down. And if the forward rate of reaction slows down, we didn't do anything to the reverse, did we? But if the forward rate slows down, then that means the reverse rate must be faster now because they were once equal. Now I've slowed down the forward rate, so the reverse rate must be faster. It's going to start shifting backwards. A way to remember what's going on here, just a quick little thing here. If we make something tiny, we're going to shift towards it. Right? We made A tiny. We shifted towards it. If we now watch the spelling here on enormous. If we make something enormous or big, we're going to shift away from it. Look, We made D enormous. We shifted away from it. Over here, we made B enormous. What do? We shifted away from it. If we were to make C tiny, we'd shift towards it. Okay, so tiny, you make it tiny, you shift towards it. So if you remove it, you shift towards it. If you add it, you shift away from it. Looking at this guy from a perspective of a graph, we said, okay, let's look at the one where we removed A. So we're going to make A tiny. So this time we're seeing a drop in the concentration of A. So A is removed. And the effects of this, of course, is that the system tries to get this back to normal, but it's never going to get back to where it originally was because we got a new balance. The consequence is that B goes up, and because we're shifting in the reverse direction, remember, right? We're trying to get A much larger. This guy goes down, that guy goes down, that guy goes up. So what we're going to see then is that C begins to drop and D begins to drop until we're back at our new happy place. We're back at our new equilibrium. Everything is happy. Everything is balanced. There's no changes. Forward rate equals reverse rate. And we know that because we're seeing it. All right, so we're in a new state of equilibrium here. We have a period of adjustment. That's that stressful period, remember, when everything's trying to adjust to the new place. So there's an adjustment time. How long that takes, of course, depends on how severe the stress is, how fast the chemical reaction can respond to the stress and things like that. And again, once we have that adjustment period over with, now we have a new equilibrium at a new position. Everything now has accommodated this change. All right? Everyone's in a new happy place. Okay, here's another example, and we're looking at this and saying, okay, based on this graph, which way did the system shift? All right? So we're looking at this graph and we're saying, oh, here's the stress. So the addition of hydrogen is the stress. We've added hydrogen to this system, so I'm looking at this reaction up above and I'm saying, okay, we just made hydrogen enormous, made it big. We want to get rid of it. The only way we can get rid of it is the shift in that direction. Is this making some sense? Well, if we shift in that direction, the NH3 should go up. Did it? Yes, it went up. And the N2 should drop because we're moving forward. Did it? Yes, it did. It dropped. Now we're at a new balance. Okay, temperature. What's going to happen if we change the temperature of a equilibrium system? Well, in temperature, there's a couple ways we can look at this. You can look at the endothermic, exothermic business, and I'll look at both ways, but you can also consider temperature to be like one of these A, B, C, or Ds. You know, if we add energy, then it's going to shift depending on what side the energy's on. So let's have a look at it. Okay, if something is endothermic, I'm just going to quickly drop down here to this. Again, we're looking at this and we're saying the addition of the extra heat is going to favor an endothermic reaction. And the idea behind that is the direction is going to be endothermic because the extra heat is going to have to be absorbed. This time the stress is the addition of the energy. And it's going to have to get rid of that excess energy, so it's going to shift in an endothermic direction. So I like looking at it from an A, B, C, D perspective, and I look at the energy as if it's a reactant or product. And I'm saying, all right, let's put this guy in a hot water bath. Let's boost the energy up to almost twice as much energy. This system is now uncomfortable. It wants to be in a state where the energy, you know, is about 92 kilojoules. We've just put it in a hot water bath where we boosted up the energy. This system is stressed out, saying, man, it's too hot here. Let's get rid of some of this energy. So to get rid of the energy, it's going to shift away from it. Remember, we made this enormous. We're going to shift away. Let's get rid of it. So we get rid of it by shifting in that direction. The consequences, just like before. We're going in the reverse direction. This guy's going to go down. These two are going to go up. Okay? The idea being here now from the collision theory, we just explained it in terms of Le Chatelier with the stress. But from the collision theory, we're saying, hold on now. If we increase the energy here, if we put this in a hot water bath, we should increase all collisions. We're going to have more collisions that are more intense with more energy. That's true. But because this is in the endothermic direction, it's going to absorb energy. What we're saying is the reverse rate is going to be made more favorable. It's going to have more successful collisions because of the increase in energy. All right, and that's what the collision theory would say. We're favoring the reverse direction. The exothermic system is if we made it cold. All right, so let's make this reaction container very cold. Let's put it in an ice bath. So here we are in a state of equilibrium at 92 kilojoules. That's how much energy this reaction's chugging out in the forward direction. It's comfortable. All of a sudden, we reduce the energy environment that it's in. We drop the energy to 40 kilojoules, and the reaction's saying, well, I don't like it. It's too cold. And the way it warms itself up is to try and produce more energy. And this is what we mean by saying it's going to go in an exothermic direction. If we make it cold, it produces more energy by going in an exothermic direction. I like to look at it from my ABC again. In this case, we made D tiny. We made the energy tinier. We're going to shift towards it to try and replace it. All right? So we're going to shift towards the energy drop. So two ways to look at it. And again, Le Chetalier would say the stress, all right, we made it small, we want to get it back up again. Collision theory would say, all right, we just decrease the energy, we're going to slow down all the collisions now. Every single collision here is going to be slower with less energy. And we're saying, yeah, okay, but the fact of the matter is the forward and reverse rates are going to be slowed down, but the forward rate is going to be more favored because it's going to be producing that energy. All right, it's not going to be that slowed down as much as the reverse. Okay, if we look at this from a graphical perspective and we say, well, what's this graph going to look like here? And we're saying we're not going to see any spike this time because we're not adding any nitrogen or hydrogen or, in this case, ammonia. We're not adding any of these reactants. What we're going to do is simply put this in a hot water bath. And we're saying, hey, if we put this in a hot water bath, what we did was we just made the energy much bigger. And by making the energy much bigger, this system is going to want to shift away from it, get rid of that energy. The consequences of shifting away is that NH3 drops, hydrogen will go up, and nitrogen will go up. So from a graphical perspective here, what we're going to see is exactly what we just described. The hydrogen is going to curve up and then level off to a new equilibrium. The nitrogen will go up and then level off at a new equilibrium. And because we're shifting in the reverse direction, the NH3 is going to drop and then level off to a new equilibrium. So we can see that a new equilibrium is achieved. And again, there's an adjustment period there, right? That's the period that the stress is being taken care of. And that's the adjustment period. The important point is we're at this equilibrium before, the stress was taken care of, and now we're at a new equilibrium. And like the other graphs, this one doesn't have any spike. We look at these other graphs back here, we added hydrogen. You see the spike? Over here, we removed the concentration of A. We dropped the concentration of A, so you see a downward spike. All right, in this graph, there is no spike because we didn't add any of these. That was not the stress. The stress was the temperature, the energy. Okay? And we know the system shifted in reverse because the hydrogen went up and the nitrogen went up, and that's how we know. Okay, the effect of pressure. Pressure is really only going to be affected equilibrium systems that have gases in them. Okay, so only systems that have gases we're going to consider for pressure, and the reason for that, of course, is if you take something like you know, a bottle of Pepsi that's completely filled and the stopper's on, and you try and squeeze it. You can squeeze it a little bit, and what happens is the Pepsi goes up and compresses the air that's above the Pepsi in that bottle, just that little tiny air pocket. So you can compress that, but once you compress that, it's very difficult to squeeze it anymore. Because once the bottle fills up, the empty space is filled up with liquid, the liquid will no longer squat together. You know, you take something solid and try and squeeze it together, like a bottle full of sand or something. It won't squeeze. It's incompressible. So no matter how much you change the pressure on a liquid, it's not going to compress it. All right, it's not going to be able to squeeze it together. So no effect on solids or liquids, only on gases. And the idea here behind Le Chatelier's principle in gases is it says when the pressure on an equilibrium system is increased, again, that's going to be the stress, too much pressure. The system is going to try and shift to get rid of that pressure. And what Le Chatelier is saying is that if we can shift to a side that has less gas, that means less pressure. If we have 1 mole of gas versus 2 moles of gas, the 2 moles of gas wants to occupy twice as much volume. If it can't, if it's trying to occupy the same volume, then 2 moles of gas is going to have twice as much pressure as 1 mole of gas. So Le Chatelier would say, hey, if you want to relieve that stress, if you want to relieve that pressure, make less gas. All right, let's see what this has to say here now. Okay, so if we have a stress where we increase the pressure, Le Chatelier would say let's shift to the side with the fewest moles of gas. We want to relieve the pressure. If the stress is the opposite, we decrease the pressure. Le Chatelier is saying, hey, not enough pressure, let's make some more gas. More gas, more pressure. So if we decrease the pressure, we're going to shift to the side with the most moles of gas. We want to get the gas pressure back to normal. Now, if the moles of gas are equal, if we have 2 moles of gas on the left and 2 moles of gas on the right, then there's really not any advantage. By shifting one way or the other, we're not making less gas to relieve any pressure. So if the moles of gas are equal, then you're not going to have any effect on the equilibrium. Okay, so here's an example. We've got this reaction where we've got nitrogen plus 3 moles of hydrogen gas produces ammonia gas. Now, if we add up the number of moles of gas here, we've got 3 and 1 for a total of 4 moles of gas on the reactant side and 2 moles of gas on the product side. So if we increase the pressure, the response is to try and get rid of that pressure. And we know that if we make less gas, we have less pressure. So if we got too much pressure, shift to the side with less gas, and that means we're going to shift to this side. So the reaction is going to shift forward, and that's going to relieve that stress, and therefore we relieve the pressure. We got less pressure. The system is now a little happier than what it was before. Okay? Again, if we look at this graphically, what we're going to see that if we decrease the pressure, we know that we're shifting from 4 moles of gas to 2 moles of gas. Hold on now, I think I got something messed up here. Let's have a look. There we go. A decrease in pressure will cause the system to shift to the left and attempt to produce more moles of gas this time. So remember, the stress is opposite to what we said a minute ago. We're decreasing the pressure. We want to get the pressure back up. We get the pressure back up by making more moles of gas, 4 versus 2. So what we see here graphically is that if we're shifting in the reverse direction, the nitrogen goes up, the hydrogen goes up, and in this case the ammonia goes down once again. Okay? And what we've done here now is we've achieved a new equilibrium. We know that everything is leveled off again. We have a period of adjustment in between. We have a new equilibrium. Everything is balanced off again. And we can see that there's no spikes, right? There's no spikes here because nothing has been added or gained or removed. It's simply the fact that we've changed the pressure. Okay, gas volume. What happens if we change the volume of the container? Well, we have to look at something here called Boyle's law. And Boyle's law is just a simple little law saying that if I have this container and I push down this piston, I'm going to cause this same amount of gas to be occupying a much smaller volume. So these guys are going to start colliding together more frequently, and the pressure is going to start going up because there's just no room there. So the idea behind this is that if I decrease the volume of my container, I increase the pressure. So it's an inverse relation. If one goes up, the other goes down. Okay? If I pull back out on this piston, I'm making a much greater volume, which means now the pressure drops because there's more space for this gas to occupy. So now it's going to have fewer collisions, and therefore we're going to have less pressure. So if we increase the volume, we've decreased the pressure. Let's look at a couple of examples here. The very first one I want to look at is the idea of being able to boil water in your bare hands. Okay? In this case, what we're looking at is the idea of taking liquid water and vaporizing it to form gaseous water. Now you notice here there's no gas on this side, so I'm saying 0 moles of gas versus 1 mole of gas. So what I'm going to do is I'm going to put a small sample of gas in a container, little syringe here, and I'm going to pull out on the syringe. I got a little tiny bit of water here. It's stoppered off on the bottom so that no air can get in. And what I'm going to do is pull out on the syringe. I've increased the volume, and this is going to cause a decrease in pressure. All right, how is this system going to respond if I decrease the pressure? Well, it should shift to try to make more gas, shouldn't it? If I decrease the pressure, it's going to want to make more gas. The result of wanting to make more gas is that it's going to shift to the side with gas instead of liquid. And what we're going to see then is it's going to shift to the side to try and fill up this container. So it's shifting to the side with the gas to try and fill all this empty space with water vapor. So in a sense, without changing the temperature, we've boiled, vaporized the water by simply reducing the pressure. All right, we see the water vapor starting to condense on the sides and bubbles forming here. Okay, here's another example. Okay, we have another equation here where we've got N2O5 going to NO2 and O2 plus some heat here. Don't worry about the heat. We've got 2 moles of gas on this side, 5 moles of gas on this side. I'm keeping the temperature constant. That's why I'm not going to worry about the heat. Temperature is held constant. I'm going to increase the pressure. We increase the pressure by pushing down on that plunger. We got less space available now. By pushing down on the plunger, we've got less space. We got more pressure. We want to get rid of the pressure. We want to have less gas because we want to occupy less space. So what we're going to see then is a shift in the reverse direction. We want to shift to make less gas. So we're going to shift in that direction because we've increased the pressure. Less gas, less pressure. Okay, another example. Here's another one. We're looking at this guy and saying, okay, we've got iodine plus chlorine gas going to ICl gas, and we see there's 2 moles of gas on this side, 2 moles of that side. We decrease the volume of the container. The effect of that, remember, if we decrease the volume, it's inverse. We increase the pressure. We want to shift to the side with less gas. Well, what happens here? Even though we have an effect of pressure, we're not going to see anything happening here because we have equal moles of gas on each side. There's no advantage. So no shift. The next thing we want to look at is the catalyst. Now we know that reaction rates are responsible for shifting equilibrium. If the forward rate is somehow advantaged, then the reaction shifts forward. If the reverse rate is advantaged, then it shifts backwards, and vice versa. If we lower one or the other, then it's going to shift because of the reaction rate. So we're saying, okay, what about catalysts? Catalysts work by lowering the activation energy. It lowers the barrier for a chemical reaction. We're saying, so a catalyst is working on reaction rate. So what's going to be the effect on equilibrium when we add a catalyst to the system? And we're saying, okay, let's look at the diagram of what's going on here. Here's a typical reaction. Forward direction takes a energy kick to get it going. If I want to reverse this reaction, I have to kick it back. I add the catalyst here, and it lowers the energy in the forward direction, makes the forward reaction faster. Well, if we look at this from the reverse reaction, say, hey, we just added the catalyst. Isn't that pathway still available? Instead of going all the way to the top, let's choose the catalyst route. So in a sense, the catalyst is making it easier for the forward reaction, but it's also making it easier for the reverse reaction. And the idea being is it's making it easier by the same amount. So it's speeding up the forward rate by the exact same factor that it's speeding up the reverse rate. There's no advantage. So the idea behind a catalyst is, yeah, you can add a catalyst. It's going to have no effect on the position of equilibrium because we're not favoring forward or reverse. We're favoring both of them the same, which means we're not favoring either one at all. So therefore, it's not going to affect the position of equilibrium. It's only going to get us to equilibrium quicker. What I mean by that is if we go back and look at some of these guys right here, this adjustment period is now going to take a lot less time because the amount of forward and reverse, right? This is going forward, reverse, forward, reverse, forward, reverse, forward, until it gets here, at which point the two are equal. What's happening with a catalyst is it's going to make this time frame a lot quicker. So it's going to get us to this new equilibrium much more quickly because it's speeding up both the forward and reverse. That's the only effect. This position before we add the catalyst is going to be the same for these guys. We add this, it makes the time period shorter. The position here should be the exact same as we have written, whether or not we add a catalyst. Whether a catalyst is there or not, it should be the same. All right, it's not doing anything to the position of equilibrium. Same is true for surface area. Surface area speeds up both of them for the most part. So by changing the surface area of a solid is really not going to affect the equilibrium position. It's simply going to get us there quicker. All right, so very important footnote here. The catalyst and surface area have no effect on the position of equilibrium. They simply get us to equilibrium quicker. Okay? Very important point. They're going to try and tangle you up on that one for sure on the multiple choice, on the public exam. So catalyst and surface area have no effect on the position. They just get us there quicker. Okay, here's a typical question that you normally would see, something like this. It's saying, okay, as a written question, is saying, here's a chemical system at equilibrium. What could we do to maximize the production of ammonia? In other words, what can we do to make this reaction system, this equilibrium system, what can we do to cause this guy to shift forward? All right? Now this question would typically be worth 2 or 3 marks, so you're looking at this and saying, okay, what things could I do? Well, we want to try to explain this in terms of Le Chatelier's principle or collision theory. Sometimes he'll tell you which way to do it. But the idea behind this is under normal atmospheric conditions, this reaction really doesn't want to go forward. Nitrogen is really not that much into chemical reactions. It doesn't want to do this under normal atmospheric conditions and normal temperature. So the question would be, how could we make this reaction go forward, so assuming we want ammonia for some kind of industrial purpose? In fact, they wanted it for making gunpowder and whatnot, so they wanted to make as much of it as they could, as fast as they could. So the very first thing we could do is say, all right, the obvious things would be, let's increase the amount of nitrogen. That'll get the reaction to shift away from nitrogen, so it'll shift in this direction. We could also add more hydrogen. Well, you're going to do that anyways because you want to make as much of this stuff as you can. And at the same time, we want to remove NH3. And by removing NH3, the reaction is going to be pulled over. Yeah, well, that makes sense, right? So those are three concentration adjustments you could do to shift it forward. What are the less obvious things that they're looking for here? Well, we know that there's an energy component here. So the idea would be, well, let's get rid of some of this energy. And the system is probably going to shift forward here saying, hey, if you make the energy tiny, let's get rid of some of this, put it in a very cold conditions, ice bath. This guy's going to try and produce more energy because it's cold. It wants to warm up again. So we're going to shift it forward by decreasing the energy. Okay? Now, the only thing here is that by decreasing the temperature, you're going to slow down the number of collisions. So you might think, well, that would be kind of opposite to what we were taught in the other lessons. All right? But what we're saying is this reaction really doesn't want to go forward anyways. It's not going to happen. But by having it at colder conditions, we're making the reaction more favorable to get it to shift forward because of the drop in temperature, because the forward reaction is favored under cold conditions. Okay? The problem, of course, is we don't want to make it so cold that we don't have any successful collisions at all. All right? So there's a trade-off here. The other thing we can do is to increase the pressure. And if we increase the pressure, the system is going to shift to the side with less moles of gas. And we notice that on top here, we've got 4 moles versus 2 moles of gas. And remember now, these are for gases only. If there's any solids in these mixtures, you don't count the number of solids, you only count the gases. So we increase the pressure, we want to shift to the side with less pressure, that's forward, and there we go. If you look in your textbook, the conditions that are favored here are extremely, extremely high pressures, up to 20,000 kilopascals, very, very, very high pressure. And at that high pressure, there's a great big safety concern. And the optimum temperature is around 400 degrees Celsius, which is really quite hot for the most part. You know, water boils at 100. But you know, from an industry perspective, we could easily have a chemical reaction happening at, say, 900 degrees Celsius. But at 900 degrees Celsius, this reaction would be much slower than we would expect it to be. It would be much quicker at 400 than it would be at 900. Okay, so the answer to this would be, what favors the forward reaction? Low temperatures and high pressure, because of Le Chatelier's principle.